Okay. So this is essentially the last little lesson on static electricity, not required for our quiz, but discusses some uses, some examples of where static electricity is used in industrial uses, maybe home uses, and then examples of static electricity that you may have noticed or encountered in real life. So uses and hazards of static electricity, and I'm just going to start by listing them and describing them. Now, I do have demonstrations that go with most of these things, but they involve me firing up the static electricity generators, whether it's the Wimshurst machine, which we know very well, or the Van der Graaf generator, which I got running last night, which is good. And if I were to do demonstrations right now as I'm recording things, static electricity going through me, past me, through my microphone, zap, that would probably be the end of that device, all right? So if you're going to volunteer as we do demonstrations later on in the class, again, you want to make sure that your phones are in your bag or not on your person, because if if electricity were to go right through it, it could damage the parts. So I'm going to do all of the lessons, and then I'm going to go back and show you the demonstrations. Electrostatic painting. Now, this is used quite a bit in the automotive industry. So the paint is given a charge as it leaves the nozzle. So I'm going to use my expert artistic skills to do my best rendition of a car, because I never took any art. Are you kidding me? There we go. Look at that car right there. And we don't need any wheels on it because we're just painting the body of the car. And so what the manufacturer will do is they will connect that particular part of the car, say, to a positively charged object, making the metal positively charged. All right, I'm not going to draw electrons in this time. It's positively charged. And as they spray the paint out of the nozzle, it's my attempt at a nozzle there, the nozzle itself is negatively charged. So as the paint comes out, it's also carrying negative charges. And that paint then, the little drops of paint will stick to the car, right? Not too surprising, which means there isn't any or hardly any lost paint. So the paint then ends up sticking to the car, all right? And I would say that all industrial painting is done this way anymore, right? If you have an industry that's painting, whether it's cars or bike frames or pots and pans or who knows what you paint, maybe you don't paint pots and pans, I don't know. This would be done this way. It saves on paint. You don't have what's called overspray, the spray getting away and landing on something else, okay? So there's an attraction, and the paint sticks. We don't lose any. And again, I can do a demonstration of that in a moment. I'll put a bar here, and I can make it positive or negative, and then I don't have paint, but I can send some particles toward it, and we can see the way it behaves. All right. Am I good to go? Allie just handed in the test, so she's desperately trying to get that in. What's that? Good plan. Am I going ahead? We're going ahead? All right. Next one. Electrostatic precipitators or filters. Now, again, used in industry to remove little particles from exhaust. Say from maybe they're doing they're doing what is called smelting, where they're trying to remove the metal from rock. It involves a lot of heat. It involves a lot of exhaust coming out of big smokestacks. And there tends to be little fine pieces of material in there. And they will install what is called an electrostatic precipitator. Now for my picture on this one, well, I'll let you write and then I'll draw the picture. they filter electrically, it filters electrically charged parts. I'm not a fan of that. It uses electrically charged parts to filter. These parts attract dust and other pollutants, such as air, as they move through them. And they're used in chemical plants, and I've even seen them in home furnaces. All right? And I should have read that note. I'm not a fan of the way that words. It filters by using electrically charged parts. These parts attract dust and other pollutants. And by the way, the dust and the other pollutants are neutral. They are neutral objects. And I'll draw that on the picture. And again, like I said, they're used in chemical plants or even smelting plants or things like that that are producing any exhaust. Now, the way I'm going to draw this is I'm going to attempt to draw a cylinder, right? So I'm going to use kind of an oval at the top and two straight lines down on the bottom, as if I'm drawing like a cup or a glass. In the example that I'm going to use this mesh, this chicken wire, they call it. I just made it into a cylinder. And I'm going to put it on top of the retort stand here. And that's because in an electrostatic precipitator, there is an outside container or mesh, and then there is an inside rod. And I'm just going to put the rod like this. Now I'm going to put a dashed line, and then I'm going to have the rod come out the top. Okay? And they will make, by connecting this rod, one of the ends positive or negative. Let's just make it positive for no reason. The outer cylinder made negative. All right? And if I have a particle in here that's falling through here, and I've made the particle really big, but this is a tiny little fine particle, if I put my charges, and I'm just going to put 2, but I'll have plus, plus, and then the minus and the minus. Now notice where I put them. I put the plus close to the negative, and the minus is close to the positive. Because what that's going to do is, it's going to cause that particle to stick to the side. All right? If I had a particle on this side closer to the rod, again, we would get an induced charge separation, and this guy would stick to the rod. All right? In other words, those neutral objects would stick either to the center or to the side, just like we saw them stick. After a while, they'd have to shut off the machine. They'd shut off the charge. The particles would settle out. They remove them. They turn the machine back on. All right? And I've heard home furnaces with this in it, because you can tell that the home furnace has it in it, because you'll sometimes hear the machine arc. It'll make little zaps, right? And that's because it needs cleaning, because it's collected so much stuff, it's able to now arc across, okay? All right, so that is a precipitator. In other words, it's removing the substances, or essentially it's a filter, okay? And again, I'm going to simulate this. I'll connect it to the Wimshurst machine. We'll generate some charge, and we'll see if we can get some stuff to stick to it. Again, I'm not sure where we're at. I'm going to advance. If we're totally way off, tell me to go back. Am I good to go? You may not know this, but your photocopier / laser printer, which are really the same thing, also uses static electricity. So inside a photocopier or laser printer, there is a part that is called the drum. Not like to beat on a drum to make music, but more like a big cylinder, like a big oil drum. That's probably why it's called that. And this cylinder, And again, I'm going to attempt to draw a cylinder. So I'm going with two parallel lines like this. Again, I'm going to use my oval on one end, and then I'm going to put the other kind of half oval on the other end, if you kind of see what I'm talking about. And this is what the paper runs over, okay? And the laser, all right, and I'm just going to put here laser. The laser will fire a beam across the drum that's controlled by what you want printed. So the laser has an ability to aim, all right, and it puts the letters across the drum very quickly, okay? And it makes the surface of the drum become charged. Because lasers contain light energy that can kick electrons off of things. That's a little bit of chemistry. That's a little more than what I've taught you. But lasers are light energy, and if you shine the right light energy onto a surface of a substance, its electrons can get ejected and cause a charged spot on that drum. All right? It has everything to do with chemistry. We'll talk about that in chemistry. Yes? No, it's not because of the laser. Okay, so what happens next is a machine sends toner on it, which is the black stuff, right? And the toner is a powder, and it's a neutral powder. So when they put the toner on it, so maybe I'll just put it this way. If I put the toner on it, the toner will stick to the charged spots. It's like static electricity. It's going to stick to the charged spots. So it will stick only where the letters are on that drum. Then your paper rolls over it. The powder is transferred to the paper, okay? And then it goes into another part which has a heater in it, and it bakes the toner onto the paper. So there's a second heated part that then bakes it right onto the paper. Okay, it does a little chemical reaction that sticks it to the paper. If you've ever worked with a photocopier and it fails, and you got to take the paper out, you might have noticed that sometimes if you get one that has been past the drum, but before the heater, you can wipe that toner right off the page because it hasn't been cooked onto the paper yet. All right? So there's a secondary process that makes it stick, and that's the hot part. Okay? Yep. Yes, it is kind of like an oven that cooks the black toner onto the paper to make it stick. But static electricity tells the drum where to put all of the spots. But yes, kind of like an oven. Thank you, Rachel. That again was an awesome contribution to the lesson. Yep. Yeah, no, it's not wet or anything. So it's not being painted on, or it's like a ink printer, which you then need to let dry because it'll be wet, right? You're right. No, it's cooked right on. It's set. It's done. Yeah, that's why you can take it right away and away you go. Yep, correct. That's exactly correct. So it's not using ink like an inkjet printer, which is really like painting the paper, right? It's sticking that toner to the paper and then cooking it right on. Okay. Grounding planes and cars. Now, you probably don't see this at an airport. You know, I like airports because I like watching planes come and go. And I try to see what they're doing. And I've never actually seen this, but I know that it is done. As planes fly through the air and the wind and the air goes over the surface of the wings and the plane, that's like rubbing two things together, air and the metal of the plane. The plane can become charged. I really don't know whether it becomes positive or negative. Let's assume that it's negative, all right? Just for the sake of our picture. So when the plane comes and lands and is ready to be refueled, they need to connect a chain to it to take the charge off of the plane or ground it, all right? And again, because I am such a good artist, Huh? 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 No, this is a plane. This is a plane. Okay. Now, the plane, here, let's put a little window in here. Right, there's our guy flying the plane. Okay, we'll put some flaps on it. Let's make it look cool. Okay, that's it. Now, let's say the plane is negative as it flew through the air, picked up some charges from some air. Now, you might think that once it hits the ground, that charge should just leave. Plane lands, stops. You'd think it's touching the ground. It should be grounded, but it isn't. Why doesn't the charge leave the plane? Yep. Because the tires are rubber, and they're insulators, and they don't let that charge leave. So here's our plane on the ground. So we take a chain of some sort. I have no idea what they do. They connect it to the ground, and the electrons leave. All right? This is important because you wouldn't want to be the guy with the fueling hose, which is neutral, go up against the metal part of the plane, which is negative, and they get a little spark at that point, right at the nozzle, because that then ends poorly, right? They'll do this for fuel trucks as well, all right? So even just a truck driving down the road or a vehicle can gain a charge. That's why they tell you when you refuel your car at the gas station that you shouldn't get in and out of the car during the winter. Because what happens as you get in and out of the car in the winter? What happens? Yep. You're rubbing up against the seat with your coat. You know how you get a static charge when you're wearing your coat. If you get in because it's cold and it fills and it goes clunk and it's done, and you get out, but you don't say touch the body of the car, you go to touch where the nozzle is, and there's fumes coming out, that ends poorly for you. All right? So you want to, yeah, come on in. So you want to make sure you're grounded. Yes? Yes, that's correct. Yes, but they're still in the air. They'd have to be the same charge. There's probably some grounding mechanism there. Whether that cone, you've probably seen videos of it, is the first thing it touches and it grounds. I'm not sure. Okay. All right. Next, the most important one here, sticking balloons to walls. This is super important to discuss. By the way, I lost my little balloon yesterday. Did somebody see my little balloon? It's in my drawer? I stuck the, oh, it is in my drawer. Hey, it's good stuff. I have no idea where my little balloon went. All right. Sticking balloons, even though I got a haircut, still got enough. Sticking balloons to walls. Let's think about this one. And I didn't even write anything down there. Let's just draw a picture of it. So here we've got the wall. All right. And I'm going to put my balloon right here on the side of it there. And because I rubbed that balloon on my hair, that balloon has lots of negatives right on that surface right there. Yeah, there's some positives, but I'm not worried about the positives right now. Okay? And in the wall, there are pluses and minuses because the wall is neutral. All right? So notice way up top here, away from the balloon, I'm putting plus, minus, because it's neutral. But when you get close to the balloon, the minus wants to move into the wall because it's undergoing an induced charge separation, just like our pith balls. Okay? So this is an induced charge separation. All right? Which means at the surface of the wall, what's the charge right up against the balloon? What's the charge, Jess? Correct, but I mean right here at this spot in the wall, how would we describe that charge? Overall, it's still neutral, but because of the repelling of the electrons into the wall, this is positive right there. Where did the negatives go? Where did the negatives go? Yep. To the other side, into the wall. They've been pushed deep into the wall. All right? So this forms a little positive charge right at the surface of the wall. Yes?
If you were to put that on the other side.
Well, you can't, because this is not a picture of a wall that we're looking side on. This is the wall deep into the wall. So I'm not talking about the other side of the wall. It's not like I'm saying I'm going to rub a balloon up against that piece of drywall. And by the way, on the other side of that wall is a bathroom. And if I ran into the bathroom, I could stick something else to it. You know what I mean? It's not like it pushes it that far. It probably just pushes it a little bit into the wall because it's not a conductor, so it's not going to push it all the way to the other side. It's just making enough of a positive charge right at the surface for the balloon to stick. All right? And it really doesn't do it very well, because look at this one. We even tried this, whoops, the slippery one. We even tried this yesterday, right? If I put the same charge on this one, can I get it to stick? Not as well. Why not? Why does this fall? Why does it fall? Yep. So gravity beats that little charge. So it's a tiny little charge. So any bit of gravity is going to beat it. The only reason that works is because the balloon is so tiny. That tiny little charge can hold it up. Yeah, question? It will depend on whether it's humid, just like when we do our static electricity experiments, and I said, you know, it's humid today, it's not going to work very well because the charge is going to leave the surfaces. So the water vapor will slowly take the charge away from that balloon and it'll ultimately fall. But if it's like super dry weather, it could stay there a long time. The surface of the balloon is very smooth. Remember we said it with picky things, the charge could jump off? That'll stay for a long time, especially if it's dry air. Okay. Last one to deal with here is lightning. Now, I had an entire video I found online. It was actually an old video that I used to show back when I used to teach this to the college physics students. And I found the exact same one. It was amazing. It's like a 10-year-old video. But I want to show demonstrations of this instead, so we're not going to watch the video. I have the video on the Google Classroom if you wanted to watch a bit of it. It is interesting. It does go over how lightning is developed, et cetera, and I'm going to talk about it here. So you can write that down, and again, I'm going to draw a picture. And I am making a video, Jamie, so you can write the stuff down. And I said I was going to do all of the notes, and then we'll talk about these things, and you might even have time to write it as I talk about them. We're going to do some demonstrations, see what it looks like. So, I don't know if you know this, but in a thunderstorm, or conditions in the atmosphere or the air that makes a thunderstorm, results in the air rising up very quickly. We say that it is an unstable air mass, all right? It happens when the area or the region is under what we call low pressure. So what I want to draw here is, let's draw the ground. That's the ground. And if we want to recognize the ground, let's put a little house here, just so that we know what we're talking about here. Funny looking house. All right. And I'm going to draw the bottom of the cloud. All right. And then you might know that a thundercloud kind of has this big shape that then kind of goes way off like that and does that. Thundercloud? Thundercloud. Yeah. Take the music out of here, Jess. Same with you, Travis. Take the music out. I don't need a soundtrack. I'm better without a soundtrack. Okay. When this happens, air rushes up. All right? There's air rushing up. That's what's causing that shape. Water vapor rushes up. It gets cold because it's cold up here. All right? That water vapor turns into droplets, little raindrops. And if there wasn't a thunderstorm and the wind wasn't blowing up, the raindrops would fall and we just have regular rain because they'd get big enough and gravity would win. But the wind is blowing so hard that it blows it up so high that they freeze. And as they freeze, they gather up more drops with them, and they turn into essentially hail. Then they get so big that gravity wins over the wind, and they start to fall. So we have some hail that begins to fall. All right? So now the hail is starting to fall. Okay? As it's falling, there are still little water drops, and you don't need different colors. This is drops, like raindrops, because they're lighter than the hail. Which way are they moving? Which way are they moving? Jenna, Lee? They're getting pushed up. And they are rubbing against the hail as it moves down. Rubbing. Friction. Just like our experiment. It's this that scientists believe that caused this separation of charge. All right? Now, some people who study this stuff know very well which charge moves up and which charge moves down. I'm not 100% sure. I think, if I recall, that the negatives move up, but I'm not 100% sure. I think that's the way it goes. And the hail, as it falls, becomes positive, and as it keeps bumping into things, in the end, positive charges end up at the bottom of the cloud. Okay? All right? So we've got a super positive thing here at the bottom of the cloud. Lightning can happen two ways. Lightning can happen like this. Actually, it would end up going the other way. I apologize. Let's get rid of that arrow. Lightning can end up happening within the cloud. It goes from the negatives at the top back down to the positives, making everything neutral again. So it's just like when I crank up the Wimshurst machine. The positives and the negatives, they separate so much until the air can't handle it and crack. It does that. Same thing here. The wind keeps blowing until the charges get so big opposite, and then crack. They get back together, and then the wind blows again. Okay? Another thing can happen down here in the earth. Okay? Just like my balloon, far away, there are equal positives and negatives. All right? But when we get close to the cloud that's close to the ground, the negatives are going to want to get really close to the surface. All right? They're getting pulled up by this. This will pull negatives right up to a tree or a house. And if that then gets stretched enough, and when I say stretched, I mean like when I crank the Wimshurst machine and the air is just hanging on, if that gets enough voltage, then crack, we get that. Okay? Yep.
Did you get friction if it's a negative on the surface? Did you like load a positive on it?
Are you saying if you were on the surface of the earth, could you make something positive stick to the earth?
Yeah.
Because the earth has now become negative? You could, but gravity pulls down as well, so you wouldn't really measure it. Are you saying maybe on the side of the building, could you stick something to it? Moments before the lightning strike, the answer is yes. But if you're standing there, being amazed that you stuck something to the side of your house, you will likely die in the next moment or two. Because that only happens just before the lightning strike.
So then you can tell when a lightning strike.
You can. If you are standing out in a field, let's say you are standing out here in the field. This is Marshall, because he's the only person as big as a house. No, I'm just joking, Marshall. Okay. If you're standing out in a field in a lightning storm, and you have long hair, not like my hair, but like your hair, if you are at imminent danger of being struck by lightning, your hair will stand on end. It will start to rise. If that's the case, you drop to the ground as quickly as you can. Actually, the proper way to save yourself at that point is to crouch down in a ball like this. Because if the lightning then does strike you, the electricity will go through your head, through your knees to the ground, and won't cut across your chest where a very important part of your body is. What important part am I speaking of? Your heart. Because it's the electricity across the heart that stops the heart that then causes death. But yes, that will happen. But if you feel that, you're in danger. You want to hit the ground. Yes. You probably would. You would hope that most of the electricity goes over the surface of your skin, because your skin might conduct it out to the bottom. If you're going to be hit by lightning, you need the heart to keep pumping too. Unless somebody's right beside you with a defibrillator, then they could take care of you. But if they're not, you're in trouble. Yes.
I can't tell if there's electricity in the striking. My hair.
No, I was going to say that your hair would struggle. You would feel some tingling, but it wouldn't stand up on end. Yes. Oh, that's fun. Correct. I believe the official term is bad luck.
Wouldn't it be good luck to still alive? Twice?
As opposed to not ever being hit by lightning? Okay, lightning rods. I got to keep going so I can electrocute you guys later on.
Yeah.
That's the last one. That's the last one. Okay. Now, this brings me to the exact thing that we've been talking all along. If you have a charged object, all right? Charges light. They like. Charges like to build up on pointy surfaces. That's me typing too fast and then autocorrect fixing that. Charges like to build up on pointy surfaces. This results in the charge in a cloud making it safely to the ground. If I have an object, you'll notice that we talked always about spheres. And that's because spheres are the easiest shape to explain electricity in. But if I have a pointy object, it turns out that most of the charges build up at the pointy end. Okay? And it's because they can get a little more elbow room at the pointy end. All right? If you think about it, if you were sitting around a campfire and it was a very small group of people and you had a small circle, your knees would bump up against each other, right? So you'd be pushing on each other. But if you then turned around and faced away from the fire, well, it'd be very antisocial. It would be odd. But if you did that, you'd have lots of room for your knees now because the circle goes out. Do you see what I'm talking about? And if you have a pointy end, then the next person is going to be way over there. You've got all this room. So electrons like the points. And that's because they can get more room. They can get more room to build up. So if I have my house here, now I'm building the house again, right? I'm not very good at building houses, but that's okay. But this time I was paying attention. I put up a lightning rod. Okay? And that lightning rod, got to put a window in the house. That lightning rod is connected by a wire that then gets buried deep into the ground. That's a ground symbol right there. And so when that charged cloud comes over top, don't mind those things up there, that has all kinds of, we had positives on the bottom, right? Positives there. Then all of those negatives are going to want to build up right there. Okay? And instead of it going crack, it actually allows the charges to safely get to the cloud without a big spark. All right? And so it actually lets the charges get back to the cloud without a big crack. And it does it safely. Yes?
In theory, since pointy
Yep.
like,
Yep. Yep.
if you just didn't have the pointy thing, then your house wouldn't get struck by lightning.
No, that's not true. That's not true. Because if the charge is big enough to pull those electrons up, right? Just like when I crank the Wimshurst machine, if there's no pointy part, then it's going to go crack, just like the Wimshurst machine does. But if I put a pointy thing there, then as the electrons go up, it's not going to get to the point where it's going to go crack. The electrons are just going to go into the air. They'll just make a tiny little path into the air and make it to the cloud, and it won't be a strong crack. I'm going to show you that in a moment. Let me finish. I'm going to stop the video, and then I've got, just 20 minutes to show you some cool stuff. So we're going with a stop here. Where are my glasses?